Next presenter is Kevin Gordon of Firefly Aerospace Incorporated, entitled Firefly Alpha Flight Software Development History. Kevin.
Hello, can you hear me?
Yes.
Oh,
I can see the
excellent.
slides.
Okay, we'll just get started here. So want to thank the organizers for choosing me to present, and of course everyone that's listening, thank you. Hope you find it informative. Next slide, please. So my keynotes of this presentation, this quote is actually from me, but I didn't know a better way to do it. It's been my experience on several programs. I'm saying that, software is often invisible to a program, even though it's many more times complex than a vehicle itself, and in certain ways for obvious reasons, because it is invisible until there's some problem with it. So I started this software development project for this alpha vehicle. We'll talk about it in a minute, what that is. 3 years ago, actually it was January 3 years ago, with nothing. And this is a follow-on presentation to one that I gave 2 years ago. So for those that listen to that presentation, this is what happened since that time. But I wanted to make sure that the flight software would remain invisible in the context of not being the cause of a failure. So since the software was complete initially, which was approximately, we started getting into testing 8 months after I began. It's undergone a lot of development, 21 releases, 80 live stage tests. I have one here, over 1,400 seconds engine ignitions. That does not count all the test preparations like tank pressurization, the rest of it. If we counted flight software usage for those activities, it would be many, many hours. So where are we at right now? We are undergoing final certification testing for Flight 1, which will be upcoming from Slick 2 West at Vandenberg. Next slide. A little bit of background about Firefly for those of you who don't know. This is sort of the second incarnation of the company. We're headquartered just north of Austin, Cedar Park. It's still the Austin area. It's that little top picture. That's engineering facilities. There are manufacturing and test facilities at Briggs, Texas, which is about 30 miles north of here, kind of out in the middle of a cow pasture, without cows though. Let's see, down here on the bottom, there's integration facilities. I'm talking about the photos. That's Vandenberg HIF, horizontal integration facility, and that's our Slick 2 West launch platform. So the company is led by Dr. Tom Marcusic, and we have some high profile, I didn't list them all, but the board of directors is pretty impressive. Former Secretary of the Air Force. Advisory board includes William Reddy, who's Office of Space Flight Associate Administrator. There's employees here from just about every aerospace company and government agency, U.S. that has been in effect. In fact, I started at myself, Lockheed Skunk Works, and is quite a few years at Raytheon Missile Systems. So the first, Firefly has a vision to provide low-cost access to space for small payloads, and there are other projects, but that's not the focus of this talk. And we're going to talk about Alpha and the flight software. So next slide, please. A little more about Alpha specifically, just some key points, and I'll point out what these photos are. The one on the left was actually the stage 1 ATP testing that went on at Briggs. The top small photo, that's where they're testing the Reaver engines at one of the test stands, a horizontal test stand. I believe this other picture is when they were getting ready to ship to California. So some key points about Alpha, pretty impressive. The structure, I think it's the largest all carbon structure that exists. It was designed, produced in-house. The engines, design, manufactured here. Of course, you can't, it's kind of hard to go buy a rocket engine. This key point about avionics is pretty important that I'll talk about with the software, predominantly COTS. We didn't want to reinvent the wheel for everything. So performance, low Earth orbit, 1,000 kilograms, and sun sink, 630 kilograms. Already mentioned first launch upcoming, Slick 2 West. Next slide, please. So what does the flight software do? I'll start with the bottom. It operates the vehicle. So the GNC steers the vehicle. The flight software proper operates it. And the way it does that, it collects sensor data from onboard sensors, does engineering conversions for use by different applications that are part of the flight software. And I'll talk about those applications in a minute. And directly operates valves, tank valves, all kind of valves. Rocket's a pretty complicated thing. Also, safety critical functionality like stage SEP, fairing SEP, payload SEP. Structure and timing for all applications, including GNC. Okay, next slide, please. Sorry, I'm just checking my time. What approach did I take when I started this? Simplest, soonest, because we were really driven by test requirements. This is very atypical of any software program I've been on, and I've worked on software systems for advanced military aircraft, satellites, missiles, tactical missile systems. This is actually my first launch vehicle program, but given the short amount of time we had, we didn't want to reinvent any wheel. So looking for off-the-shelf BSP, we didn't want to get into the BSP device driver business. So that's the approach we took. Rapid prototyping and development to support testing and avionics that was coming online that didn't even exist. In fact, I ended up emulating avionics with VxWorks RTPs in many cases just to make sure things were working. Make the flight software flexible. And I'll talk about how we solve that in a moment. We chose VxWorks just because it's rock solid, and we felt like at the time it was the best choice for us, and that's kind of proven out. I already mentioned a COTS flight computer with all necessary device drivers. This other bullet's kind of interesting, and my history in all these other programs, we are taught. I was always taught these monolithic kernel builds. I had the opportunity on this program, though, to really look what VxWorks offered, and it made sense to me to move into user space. And so that's how we implemented these applications. They're in user space. C++, someone asked me the last time, why C++? It turns out, if just by metrics, if you look at the code, there's some 37% of it that's used across different applications, and of course that was aided with C++ classes. The next one's kind of interesting. A lot of programs will do core affinity, and maybe that's for absolute determinism, although it's interesting, even though without core affinity, we can reproduce the same outputs if we have all the same inputs. So it's not like the VxWorks scheduler is changing its mind depending on what time it runs. I already talked about fully configurable. This last one, I want to make sure it's clear. Decided to go the asynchronous route. And what I mean by that is asynchronous between applications except where required. Obviously, there's synchronous task execution going on with an application, but that prevents, and my experience from some of the programs where the software fell apart like a deck of cards when something didn't happen. For example, the receipt of some sensor measurement prevented something else from running, that cascaded down. So we have some intelligence built into our applications to deal with either stale data or data that doesn't show up, period. Next slide, please. It's kind of an overall hodgepodge diagram showing the flight software. This black box that you see in the middle represents the flight computer. Over on the left, this is kind of interesting. So we have a net boot. What's on the flight computer is really a two-stage bootloader, and the operating system, all the flight software applications, and there's a bunch of configuration files. I mentioned configurability was one of our main goals. That's actually a repo. So it's a very easy way for us to configuration control, really version manage in this case, the software that's going to be loaded on the rocket. We know exactly what it is. It's a Git repo. So pretty easy to figure that out. So right, we've got 11 configuration files. We can configure each rocket. We can also configure between facilities, so running in the hardware in the loop. If we want to do a special test, or there's a special test at Briggs, it's just changing in particular, usually like a state machine configuration file. All right, so there's two network switches on the rocket, stage one, stage two. There's only one flight computer. It's on stage two. It controls both stages. On this little Alpha rocket image, you see a sensor coming in through the switch, going over through the VxWorks. This light blue color is meant to be like the kernel. We're in this greenish, different greenish color in user space. So we have a bunch of applications, separate applications running. They communicate data primarily through VxWorks shared data objects. And we wrapped our own C++ classes around the existing VxWorks mechanisms to provide multi-layers of security and making sure that was robust. Back to this user space paradigm, we do share, of course, resources between the kernel space and user space, but we don't have the adverse effects of being able to stomp on the kernel and crash the entire system. Same thing for these applications. The shared data objects is really just overlap virtual memory, but they cannot step on each other's code. And in fact, if we design this, we can start any of these in any order and they'll function. Now, they need, in most cases, more data to function correctly, like GNC. See anything else on here? I think that covers that. And we have effectors and devices going out for the flight software. Okay, next slide. Better speed it up a little. So, even I mentioned this is a different animal than I've tackled before, because we were not, our development process isn't driven by releases that we have planned out based on how we wanted to do things necessarily. It was driven by stage test campaigns. So what we call a release is really based on that. And I won't go into the gory details of this slide, but it wasn't wild west by any stretch of the imagination. We used industry standard tools. We had good process, good configuration management, version control. What this really shows is a cycle that continued from the start, where we would understand what the test campaign requirements were. We'd have planning, use Jira for issue tracking, use Bitbucket, I'll talk about that in a minute, for the actual implementation that was required for those work products, and version control for the release artifacts for the particular test. Next slide, please. Only have 5 minutes. I need to move quickly here. This is by no stretch all the tools we use. I've already mentioned we use the Atlassian tools, Confluence, Jira, and Bitbucket together, integrated together, to help us execute our work. Of course, I mentioned we use VxWorks, so of course we were using Workbench. And System Viewer was very useful. That's that little picture here on the bottom right, to understand the performance. We did not have a simulation environment. We did all the development directly on the flight computer because we had little time and had to make sure things work properly on the target hardware. Next slide, please. How we do verification validation. So verification, validation is supposed to be in the intended environment. We'll talk about verification, very straightforward, pull requests, formal peer reviews of changes in code. We have a good static analysis tool. We happen to be using C++ cert rules, which we like as compared to others. We have other specialized tools. I mentioned all those configuration files. So we have a tool that checks the syntax of all those to make sure the flight software will like them. So what am I saying here? Yeah, of course we have hardware in the loop, but I think Steve mentioned it's critical to have super high fidelity. Absolutely, certainly. It's hard to do for a rocket, though, and it's hard to do for a startup. So we did the best we could. We modeled things where we didn't have like a rocket engine to the extent that we could to test. But, the truth be told, we really couldn't do fully integrated validation testing except on the integrated rocket. And that's what we did. Last little blurb here, we have so to assess how the flight software operated, you have ongoing stage testing that may try hot fires, 10 times in one day. We have to understand what the flight software did. So we put together a pretty slick tool we call Rembrandt that takes all the telemetry and gives us a good view of what happened for that particular test case. Next slide, please. Progress to date. So this is from I already mentioned we started January 2018, where I put bootloader and first kernel build together in a month. Completed all prototypes. That's what I wanted to do first by about 5 months of all those applications you saw. I should note, with the exception of GNC, there was a previous GNC code base that existed from the first Firefly space systems. 7 months from start, we were already doing validation testing with ground software, with that ground software interface. When I spoke, I think it was December 2018. And I was mentioning the stage testing campaigns were coming up, and they have and passed. I already mentioned 21 releases, very formalized, going through all the testing. We did complete a flight software certification test. It took us 22 days. That was May timeframe. The ATP authorization to proceed for the stages has occurred since then. The flight software performed flawlessly for those 2 campaigns. And we do have to do a final certification test for the candidate that's going to be used for Flight 1. Next slide, please. Oh, lessons learned. I have 2 minutes, so I'll try to go through this quickly. 2020 hindsight. I think
Kevin, sorry to interrupt. You actually do have a little more time than you think.
Okay. Yeah, well, I was given 5 minutes for questions.
Okay. All right. Yeah. Okay.
Not that there'll be that many, but anyway, I think I only have 2 slides left here. So I think we made excellent choices. It's the proof's in the pudding for anything, right? VxWorks has been rock solid. Haven't had any issues with it whatsoever. This is kind of a summary here. Everything's worked very well. There are a couple little anomalies I didn't put here as bullets, but those are resolved. We're not a long pole. That's often not the case for software on a program. I won't go into the details, but I'm gonna, for advice for the audience, like, expect unexpected anomalies that are just extremely difficult to understand. Network stack issues, big. If our rocket is, of course, all network communications, you need to understand all the protocols. Strange things can happen with things like address resolution protocol and timeouts and ARP tables, things like that. Okay. The last bullet here was really a huge learning point for me, because again, first launch vehicle for me, understanding to engage range safety from the beginning. We did not do that. And so it was a task that I started on about 6 months ago, engaging range safety, and they have been super helpful, finishing the tailoring. Oh, my timer's running, went off. Hazard analysis, because if you're going to launch, you're going to end up doing that. So do the hazard analysis up front so that you can identify and build in mitigations for software hazards, because you're going to have to do it one way or the other. I'm not talking about post-launch range safety, because that is involving flight termination, which I'm not going to exactly cover here. Okay, last slide. Next steps. I mentioned both stages are at Vandenberg. That top picture is stage 1 after ATP and arrival at the horizontal integration facility. I mentioned we're in certification testing right now. They are doing launch preparations at Vandenberg. They're doing integration with both stages and the payload, pad checkouts. We have an emulator on the pad right now. We're testing the telemetry system. We'll be doing a static fire and leading up to launch. That picture on the bottom is actually the control room at Vandenberg. They did a good job putting that together. Flight 2 will have some enhancements planned. Flight 3 is the big one. We've got to go to an AFTU, so the flight software team will be working on actually a NAV2 CAS wrapper as part of the flight software. So that's all I have. I didn't put my email address on here. I should give it, if you don't mind, Christopher, real quick. It's kevin.gordon@firefly.com. That's all I have. So thank you, everyone.
Excellent. Thanks a lot, Kevin. And we do have a few questions in the Q&A.
Sure.
The first one is from Guillermo Zaragoza Prus. How do you translate the design from the GNC system, assuming it is designed in common control tools like MATLAB and Simulink or similar, to the flight software running on the rocket? What are the main challenges?
It was not. It was all built C++ from the ground up. Kind of a follow-on, though, the GNC is agnostic, so we have logical interfaces in and out to from physical interfaces, so we can run that same GNC in unaltered in a software in the loop environment.
All right. And next question from Cora Jans. Did you use a subset of the C++ language?
That VX was, we're using 6.9, I think it's 6.9.4.12 was the last version. It is, I believe it's 2004 or 2008. I don't know that there's a difference. It's certainly not a more modern version, although we did, anyone can make C++ look like C. We used a lot of the features of the language, like templates and derived classes, virtual functions, things like this.
Okay. And one more question from Peter Fettleman. What did the flight software certification test entail? And was it requirements-based verification?
No, we don't have a customer per se. So we're our own customer. We made up the test. So there's a battery of verification tests. It lasts about a week. That includes many all digital software in the loop flyouts. There's obvious things like builds of the candidates and checking CRCs and all that. Then we go into a verification section. We can't test certification on the stand because the vehicle's not there. So we use the hardware in the loop simulation with Trick and do hundreds of nominal and off nominal flyouts of the vehicle. And we also have specialized tests like really pressing the state machine and the tank pressurization applications to make sure they perform correctly.
All right, and as you're wrapping that up, we got one more question from Leonidas.
Yeah, one follow-up though, it's important.
Oh, okay.
After we went through our regime with range safety, we did have to add tests for what we identified as safety significant software function. So that actually was required by the range customer, we'll say.
Okay. And our other question is from Leonidas Cosmides. Do you allow partition migrations between the different cores? If yes, is this allowed in an ARINC 653 RTOS?
I'm not a 653 expert. I know the user space model is uh, along the lines of that. Partition, an RTP can be like a partition, a real-time process, which is an application. Those tasks are global to the VxWorks operating system. So since we're not using core affinity, tasks from different RTPs can move to different cores. I'm not sure I answered that question exactly, but
So you're not using an ARINC 653 RTOS. You're using the memory protection of an RTP.
that's correct.
Oh, okay. Okay. So I think that does answer the question then. All right. Any other questions for Kevin? All right. Thanks a lot, Kevin. That was excellent.
Thank you.
Appreciate it.
Appreciate it.
And of course, if anyone does have any follow-ups with any of our presenters, you can either email them directly at the contact information they provided, or you can take it to the Slack channels.